Okay, hi, welcome everyone. Good morning. Welcome to my talk about modern typed Python in the machine learning world. I'm Johannes. I'm a machine learning engineer at GeneAI, working on the DocArray open source project, which will also be part of this talk. And yeah, let's get into it. So the talk will be roughly structured in two different parts. So the first part will be about typing in Python in general. I think most of you should be familiar with this, but I think it's good to give some background and some context for the second half of the talk. And then the second half would be about Python type hints in machine learning applications and about DocArray, the library I'm working on that's basically trying to solve some of the pain points that are specific to machine learning applications and does it with the help of Python type hints. But before that, a few words about the company that sent me here. It's GeneAI, founded in 2020, like machine learning ops and fine-tuning company with about 60 members and spread over the globe. I'm based in the Berlin headquarters and raised quite a bit of money and trying to push these tools for ML forward. Okay, with that out of the way, let's get into the technical part of the talk. So the first question is Python a typed programming language? And the answer is it is a duck-typed language. So what does that mean? So let's take a look at a few code examples. So on one side here, let me pull up my laser pointer. You can see a statically typed language like Rust, C++, Java, or whatever it may be. And the way those languages work is whenever you have a variable or whenever you pass an argument to a function, you give it a type. You tell the compiler or the interpreter or your colleague that read the code exactly what type a variable will have, and then it runs. And you need to make sure that all of your types fit together and everything is nice and tidy. In Python and other duck-typed languages, that's a bit different, right? So you can, if we look at this add function here, you can basically pass whatever you want. Anything goes. Like you just plug something in and then no one will complain, right? I said anything goes, but of course that's not quite true because there's something called the duck test. And basically what it says is if it walks like a duck and it quacks like a duck, then it must be a duck. So looking at this example again, yes, I can pass whatever I want here, but according to the duck test, those two things that I pass must fulfill certain properties. In this case, x and y, since I want to add them together, I want to form a sum, they both need to be able to be, well, added together or summed up. And then it doesn't matter what type they really have, as long as they have this property, as long as they know what the plus sign is, as long as they can work with that, then anything is good. That's basically how duck typing works. So to sum up what duck typing is in the context of Python, I think it's something that makes Python great, actually. It's something that makes it very easy to get started with Python, also from people coming from other backgrounds that are not computer science, like engineers, physicists, etc., that maybe don't want to delve into typing theory, whatever. They just want the program to work. And it's very nice for that. It's simple. You don't need to think about these types, about these abstractions. As long as two things work together, you're fine. And it's also very concise because you don't need to specify your types everywhere, wherever you go. But there are also some cons in this. So one thing is it's a bit hard to maintain because whenever you type something, whenever you write code, and you don't specify a type, then it might work, but when then your colleague comes along later or your future self that has forgotten what you did in the past, then you may not know what the assumptions were that you made at the time, right? So it's a bit hard to maintain, especially if you work in a team. And another problem is that you tend to fail at runtime and not at compile time. So what does that mean? If you have a statically typed programming language, then where every variable has a type, then already before you run your program, you will know if those types fit together in your program. With a duck-typed programming language or a dynamically typed programming language, that's not the case. So what you need to do then is you need to run your program, and then you find out if it works or it doesn't, which is a problem, right? Because you might ship your code or you might deploy, and then you find out, oh, it doesn't work, and not ideal. So it's better to fail early and have a type system that tells you right out of the gate, okay, this is not going to work, don't even try. So that's a bit of a downside of this system. So, or to put it in meme form, yeah, dynamic typing lets you sort of do whatever you want. At first glance, it looks good, but at a closer look, it of course doesn't make sense. But you can be happy quickly and be like, done, awesome. But then you will fail. Where in static typing, you really need to think about what you're doing and like make the jigsaw puzzle work before you ship it to your users. So what about type hints, right? As we've seen right now, there aren't really types that you specify in Python, but there are type hints. So nothing strict, but you can give hints about your types. So let's take another look at the example we just saw. Again, our statically typed language is over on this side, and here now we see Python with type hints. And we see that this looks very similar to our statically typed language. So every argument that we pass to a function has a type associated with it, and the return of the function also has a type. So this looks basically exactly the same. Yeah, but one thing that I want to stress again, these are just hints, right? This is out of the box, this is not enforced. This is just something you put there, and then if you pass a string instead of an int, still no one will complain. So this is just like a guide, a hint, yeah. So what is the point of this? Why do we do that if we don't enforce it? So I think the main upside of these hints is about communication, right? You communicate your intent and your assumptions. You communicate with a number of different people or things. So you communicate with your coworkers in a team, for example. So if you write this function and you put this int here, then your coworker that needs to fix your bugs will know that you thought this was going to be an int. Turns out it's a float or like a string. It's not working. You also talk to your future self. As I said, at least I tend to forget very quickly what I did in the past, and then it's a good crutch for me to write down what I thought was true in the past. And also very important for me, at least, is that you communicate with your IDE. Like you get all kinds of nice code completions and hints that your IDE, in my case PyCharm, can just spit out for you, and it makes my life much easier. And you can find bugs earlier, right? As I said before, you need some additional tooling for that because, as I said, like these are just hints. So out of the box, this is not true. But with additional tooling, you can find bugs earlier when your types don't match up. And again, this is still compatible with duck typing. So just hints. If you don't want to do this, if you don't care about static typing, you don't need to. No worry there. So let's look a little bit of how this came to be, how we moved from a language that only has variables and no types associated with it to this hybrid thing with these type hints. How did it happen? So Python 1 was released in 1991, and there were no type hints. It was just pure duck typing, in a sense. About 10 years later, Python 2.0 comes along, still no type hints. 2006, Python 3.0 comes along, still no type hints. And yeah, by the way, they used to have a really cool logo back in the day. I wish this was still the Python logo. Yeah, but people wanted type information, right? Even Python didn't provide it, but this sort of emerged in the community. And what you would see very often is people doing something like this. So you have like your add function again, and people had this need of like expressing what they expected in terms of types. So they would just write a doc string and just say, okay, my x should be an int, my y should be an int, and I'm also returning an int. But of course, this is a bit of a hack. It's not like there couldn't be different conventions of doing it, but this need sort of arose. And then basically, Python started to develop more and more this direction. This started with this PEP 3107 in 2006, which introduced annotations, which already looks a lot like type hints, right? So you can now associate stuff with your variables or your inputs into a function. But these are not type hints yet, because what you can do here, according to this PEP, is just put any arbitrary Python expression here. So you can put these strings here, you can put like full-on expressions, you can put other stuff. This doesn't need to be types. So it's not type hinting yet, it's just annotations. Yeah, still not type hinting. Then it took more and more time, and as these things tend to do, moving quite slowly, but 8 years later, finally, there are type hints introduced with this new PEP 484. Adding optional static typing to Python, big thing, 2014. And what this did is just it like formalized some of the conventions that were introduced with these annotations. And one really big thing, it introduced the typing module. So you can now import things like any or optional that let you express information about your types. Like you can say X is any, I don't know what it is, don't even try, I'm just saying, okay, this can be whatever it wants to be. Or you can have optionals, you can say this can either be a bool or none, because it's optional. So it introduced this way of working and a bunch of conventions so that people would like be able to work together across projects, across teams, etc. And introduce also more advanced features like type variables and generics, overloading, covariance, but we don't need to get into that into too much detail. And since then, the development of Python, at least the way I see it, has sort of been a story of advancing this typing system, of advancing these type hints. As you can see here, there have been a lot of PEPs introduced about types, adding more features, making things clearer. And this is really one of the areas in Python that I think is developing most quickly still to this day, which I think is very exciting. And as it says here, we've had 16 typing PEPs in the last 6 years, so there's really a lot of development happening here. So let's sum up this brief background about Python. So Python is not statically typed, it's duck typed. So you out of the box don't say what types your variables have, but these type hints sort of entered Python slowly over the last 10 years or so. And Python is adding more and more of these typing-related features all of the time. And with the introduction of these typing features, the Python ecosystem has also started to form around these features and started to really utilize these features in what I think is a really, really nice way. So I'd like to take some time to look at some popular libraries and just to see how typing works there, how it is utilized, and what they do with this idea. So one really popular project is mypy. And as I said before, type hints allow you to fail early instead of fail late, catch bugs super early. But you need additional tooling, and this additional tooling is mypy. So it's a static type checker. It just looks at all of your type hints and then figures out, okay, does it work, does it not work? Do you have a very obvious problem that you should not ship to your users? So basically what mypy does, it transforms you from this guy to this guy. And if that's something that you want to do, is up to you, of course, but I think it's very useful, and use it in my project, and it makes my life much easier. Another thing that is runtime type checkers. So instead of checking your your types and your code before you run it, you do it at runtime. So whenever something doesn't match, you fail. And don't even try to do these duck typing things of just making it work somehow. One popular project here is beartype. Okay. Now let's move to a different kind of library almost. So the two we just saw were just really like tooling for types. But in the last years, there's also been this emergence of libraries that just use types in a really nice way to communicate with the users and create really nice APIs for Python developers. And one of those is Pydantic. Just to understand the audience a little bit, who here uses Pydantic or at least knows about it? Okay, quite a few. All right. So I'd like to take a little bit of time to look at this in a bit more detail because it will come up again in the second half of the talk when I will be talking about DocArray. So Pydantic, let's stay here for a second, lets you do data validation using type hints. So you create models of your data, and then Pydantic looks at the types that you assign to your model to do data validation, data parsing, etc. So let's take a look at what that looks like. So say you are building a web app or just parsing any other kind of data from a hard drive or wherever. And you have you want to parse this data into a certain model, into a certain object that you want to work with. So in this case, we might have a user. And then we can say, okay, our user has an ID, a name, sign up TS, and a list of friends. And then what Pydantic lets you do is you assign type hints to all of these, or you optionally can infer them as well. And what Pydantic does, it takes those seriously in a way. So at runtime, it looks at the type hints and then parses the data for you according to those type hints. So when you try to instantiate a user, you can pass in an ID and the name. It will take the defaults for all the other ones, and then it will check at runtime, does it make sense? So I specified for name, or the default is a string, so Pydantic says, okay, this needs to be a string. I pass a string, my name, Johannes, and it works. For the ID, I said it needs to be an int, but what I'm doing is I'm passing a string. So that should be a problem, one would think, but what Pydantic lets you do is it automatically coerces the type into what you specified. So if you create this user with the wrong type here, string instead of int, and then print it, we see that Pydantic just converted it to an int under the hood, which is very nice. So you just sort of specify what you want, and then Pydantic does the best to take any kind of, does its best to take any kind of data and coerce it into what you want. So you can see ID became an int here, my name is still Johannes, and you can also see that I don't have any friends, but that's a different problem. Okay, then another project that's super popular right now is FastAPI. Maybe again the question, who's using it already? And yeah, a lot of people, all right, just as I thought. So FastAPI takes a very similar approach, very similar ideas, but it's a web framework for building APIs, and it's actually based on Pydantic. So again, let's take a little bit of a closer look at this as well, because it will be relevant in the second half of the talk as well. So in FastAPI, what you do is you take these models from Pydantic and you use them to define your API that you serve over the web, to communicate to the users of your API what they should send you. And then Pydantic will take that data and parse it, and you use it in your web service, as we saw before. So here, for example, I'm creating a FastAPI app, which will be served. I have a function here that represents my API. And again, I have a model from Pydantic, this Pydantic base model, and this just specifies the input of my web API. So like an item should be this item class. And then when the user sends some request and I receive some JSON data or whatever, Pydantic will take that in and parse it into this item that I've specified, which is really handy. And again, takes this typing notion very seriously at runtime, which is sort of the conceptual leap that Pydantic and FastAPI made, I think. And here just to show the popularity, and this is just not to be mean to Flask, but the point I want to make is that these type-based libraries that use types to create a really nice user experience have really been taken off in the last few years, and you can just see how FastAPI skyrocketed and is catching up with Flask very quickly. Another thing that falls into the same category, we'll not go into that much detail there, is SQLModel. So it takes the same idea of taking these types and taking them seriously, specifying models. But in this case, it does it so you can communicate with SQL databases using type hints. But yeah, also based on Pydantic, also by Sebastian, the creator of FastAPI. Similar idea, but to interface with your SQL databases. And Typer, also similar idea, takes these type hints that you specify to just create a CLI application for you. So if a function with type hints, you use Typer, it will create, based on these type hints, a CLI that parses everything very nicely, which is super cool. Okay, but what about machine learning? So far we have seen these really cool libraries, but they're not really machine learning centric anything. And my talk is supposed to be about typing in machine learning, so what's going on there? So let's jump into that in 1 second, but first let's just sum up what we've seen. So we've seen that the typing ecosystem is growing very quickly. We have all of these libraries that take types seriously, that are becoming super popular because of how nicely they are to use for the user and how much work they take out of your hands. All right. But the machine learning ecosystem, as I just said, is still lagging behind a little bit, in my opinion. So, and this is where we sort of move into the second half of the talk, where we talk more about typing in machine learning and then about DocArray, the library I'm working on. But before that, let's look at some of the issues that are sort of specific to machine learning application when it comes to typing. So if we look at the training use case here, we will be looking at the deployment use cases in just a second. But if we look at training, we have a function, maybe a PyTorch model with a forward function. We want to specify with our types, as we just seen, it's very nice. We want to specify our inputs and our outputs. So what can we do here? So we have our forward function, which does, it says it computes the matrix product, very nice. But what do I want as an input? What do I ask my user to provide as an input, and what will they get in return as an output? With the type hint system that comes with Python and PyTorch, what I can do is I can say, okay, my input should be, the first input should be a torch tensor, the second input should be a torch tensor as well, and the third, the output should also be a torch tensor, which is nice, so I know not to put NumPy arrays in there, but it's not giving me really all the information that I need. Because what I'm really interested in is like what shapes do I want here? Like if you have all of these tensors and matrices flying around in your machine learning code, and it can get really confusing to like wrangle them together, see what you can multiply with what, so you need to know what shapes your tensors have. So what you would want usually, or at least what I want, is something like this. You can say, okay, I have a torch tensor of a certain shape, and another torch tensor of another shape, so like 1, 4, 3, so this might be the batch dimension, and then 4 and 3, and here the batch dimension again, and then shapes 3 and 4. So I know I can do a matrix product of these two, and then the output will have the batch dimension again, and then 4 by 4. So this is nice. I now know that I can combine these. But what I really want is something even more general than this, because it's not really true that my inputs have to have the exact same 1, 4, 3, and 1, 3, 4. It's more general. As long as they can be multiplied together, it works. So I want something like this. I want a torch tensor where I can say, okay, the first dimension should be the batch, second dimension should be some n and then some k, and then my second input, batch again, first dimension a k, so this needs to match the last dimension of the first input, and then I have some other dimension m, and then the output will be, okay, it's the same batch dimension I had in my inputs, the n from here, and the m from here, and then I know exactly what I can put in and what I can get out. So this would be really nice to have in machine learning applications and in training use cases. And the good news is that this exists, right? There's a library called JAX typing, which is a really, really nice library. I encourage you all to check it out. And the name is a little bit deceiving because it's not only meant for JAX, it also works with Torch and TensorFlow and NumPy arrays as well. And what this allows you to do is exactly what I've just shown you, but with a slightly different syntax. So you can say, okay, I want an array of float type of a certain shape, specify your inputs, your outputs, and that's then exactly what you get. So this is really nice. So the training use case seems well covered in this sense, which is really cool. Okay, then we're done with training. Now we want to move to deployment. We want to serve our model to the web to our users. Okay, so as we've seen in the first half of the talk, the common ecosystem around this looks something like this. You have the type-based ecosystem, I should say. You have Pydantic to specify your models, you have FastAPI to serve them, and then SQLModel to store your data in your database. So what your first instinct then would be, okay, I've done my training, I've used JAX typing, it's very nice, and now I want to define my APIs. So what you may want to do is you create a model with Pydantic, as you've done before, and just take your shape annotated types of your tensors and just put them in your model, and then it won't work. Because JAX typing and Pydantic sadly don't agree with each other as of right now, so this is a bit of a problem. And just a short aside here, we've seen this problem, and I just want to make the case that I think that this problem will become increasingly more common as we move forward, because I think web apps will change quite a bit with the advent of all of these machine learning applications that we see. Just to show a few examples, if obviously all use ChatGPT and Stable Diffusion, Whisper, all of these things, and like this is becoming increasingly more prevalent, and more of us will also start serving machine learning models in the future where we may need some of these features. So these problems that I just showed and some others that I will show in a second will become increasingly more common, I think. Yeah, and just to nail it down, what the problem here really is, the problem is that in this era of multimodal AI, where you have text and images, etc., you work with different kinds of data. So what we've just seen is that we commonly work with tensors. That's what your machine learning models understand, what they take in and what they take out. But also, once you serve this to your user, you might want to take in just image data, audio data, videos, 3D meshes, anything that you may transform or return with your multimodal machine learning applications. And this is a bit of a problem because the current ecosystem is not really set up for these types, for these data types, right? Because what we currently have is not image and audio and tensor, it's like datetime and URL and payment card number, which is obviously super nice to have if you're building a sort of traditional web app. But if you're trying to serve a machine learning model, you may need more. So these are some of the problems that crop up here. So as we said, you can't just take your JAX typing annotations and plop them into a Pydantic model. That's not going to work, unfortunately. So let's see how one could work around this problem. What you could do is instead of, right, so the problem of one sending tensors, but also like sending multimodal data in general, like images, etc. So what you may want to do is instead of expecting as your input to your API, instead of taking a tensor or an image or whatever, you can just ask your users to provide URLs, right? You can ask for image URL, a text URL, whatever the case may be, and this is not a problem. Pydantic and FastAPI, they all support this perfectly. You just get a URL, you load the data, and you're happy. So you create, here I call this multimodal document with this data, these URLs in them. You parse it, you create it to FastAPI or whatever, and that's great. But then what happens in the next step, right? So you now have your URLs, but you need the actual data. And let's imagine you work with like something, I don't know, image generation or audio or captioning, or like you have different data types there. And once you want to load your URLs, you have a bit of a problem, because how do you do it? Like, usually, if you want to load an image, you need some library for that, like pill or something. If you want to load some text, maybe that's a bit easier. If you want to load meshes, you need to know what library to use for that. If you want to load videos, a different library again. And then if you combine those in one machine learning application, then you suddenly have to juggle like 7 different libraries that you all need to learn the APIs of, and it becomes a bit of a mess. So how do we do this? Not so clear. But let's say you solve that somehow, you learn all the APIs of these data handling libraries, then you're still not done, unfortunately. So the next questions are, how do you store your data in your web app? And how do you serve your app? And the conventional answers to this, if you love type-based libraries, or as I said, SQLModel and FastAPI. But again, the question is, are these really the most suitable tools for the job still? And I'm being a bit dramatic with this question because, as it turns out, yes, for many use cases, there are still excellent choices, but not in all cases. I imagine many of you that work with ML and FastAPI do serve models over FastAPI. Maybe I can get another quick show of hands. Who's serving machine learning models over FastAPI? Yeah, a few. Okay, 2 people. Oh, that's something. But many people do it from talking to people anecdotally, and they seem quite happy. But there are some instances where you run into problems doing this. So how do we solve this? What can we do? And the answer, which comes from me in a bit of a biased way, is you can use DocArray, the library I'm working on. So what DocArray does is it tries to port this type way of thinking to the machine learning world. So the way you can think of DocArray is a library for representing, sending, and storing multimodal data for your machine learning applications with this type-focused user interface. Right? So it represents, sends, and stores all kinds of different data types. Another way of looking at it is it can take all kinds of inputs, as I said, audio, video, image, text. It flows through DocArray, and this is sort of your funnel into all kinds of other things, like computational backends, as I call them, like TensorFlow and PyTorch, or vector databases, as we will see in just a second. Okay, so yeah, as I said, this is the library I'm working on. With an amazing group of contributors here, you can see the main contributors of the library. We have also around 50 community contributors that help us a lot, which is really great. And we are part of the Linux Foundation AI and Data, which I think is really cool. So yeah, I got flown in here by GeneAI, but actually DocArray belongs to the Linux Foundation. And so we don't really control the product or the project in any real way. It's really an open source project in the truest sense of the word, which I think is really cool. Okay, so now the question is, how can we use DocArray to solve some of these problems that I've just shown? And this is now the part of the talk that makes me a little bit nervous, because we're going to run some code. I'm not going to code that much, but I have a notebook here that I'm just going to show you some code. Right. And the first thing we're going to look at is the represent part of DocArray. So that represent, store, and send. Let's look at represent. And maybe you don't need to look at my Discord messages, but that's fine. Okay, represent data. So you can think of this as Pydantic with a little bit of a hint of machine learning sprinkled on top. So let's look at the code. What does this look like? Oops. Here it comes. Okay, should be fine. So let's see if the imports work. First hurdle. Let's take in a second. Not looking good. Okay. Oops. Okay, that's not great. Let me see if I can fix this while I talk about some of the aspects in the meantime. So the import's not too important, but just to give some context, in DocArray, we have this notion of a base document. And this is very similar to the base model in Pydantic, just with a sprinkle of machine learning on top. And then we have a bunch of different types that we provide. So these are like torch tensor. And the reason we have our own type for this is that we can have this nice notation of the shapes in the square brackets and work with that. Then we have different, also audio and the array, or audio torch tensor. So we have like audio features built into those. And then data-specific URLs, as we will see in a second. Let me just... Sorry? We have a LangChain integration. It's not the full feature set that is integrated, It's more about these vector databases, as we will see in a second. So let me see if I can get Jupyter back up. Is this working now? Let's try. Oops, nope. Where did I put my notebook? This is not great. Do you see it? Can someone help me?
Yeah. Stop. Yeah. Stop.
Oh, I see it. It should be here. No? Yes, thank you. Okay, we are back. Awesome. Okay, this had to happen, but I mean, I hope it's okay. I hope I haven't lost any of you. Okay, where did we leave off? Okay, DocArray, base doc is like a Pydantic model with machine learning sprinkled on top, and we have these machine learning specific data types like torch tensors, audio arrays, audio, URL, all of this sort of stuff that we will see in a second. So what can we do with this? We can model our data, right? We can say, let's model a podcast. And what this notebook does, it builds like a dummy web app for transcribing podcasts and then also doing vector search, like semantic search on podcasts. So how do we do that? So let's say our podcast has a bunch of different things. It has some audio components, it has some text, like the transcript, as I said, and it has an embedding. So for the audio, we might have a URL. This is an audio URL. Why that is useful, you will see in a second. We have an audio tensor, which is optional. We can also have a transcript URL. So if I already have a transcript, I can just point to it, the transcript itself, so like the string itself, and then an embedding, which is a torch tensor of shape, or like dimensionality 512. So again, very nice. You can immediately express what kind of shape your tensors or your embeddings will have. Let's run this. Okay, now we can create such a podcast object in very much the same way you do it with Pydantic. So we could have an audio URL. I chose the Star Spangled Banner. It seemed fitting for PyCon US, and it's transcript URL that we can use. So in this case, these are both local files on my machine, but they could also be URLs on the web. And the data handling of DocArray will just use, it can take local URLs, it can use web URLs, whatever it may be. Then we can instantiate our podcast object with the audio URL and the transcript. Let's do that. And now here comes in some of the cool stuff that we've done, I think. So as we've seen before, if you work with URLs, then at some point you will have to load the data from your URL. And what we can do here, since we have this specialized audio URL and this text URL, we can just call podcast.audioURL.load. And it will just take the URL and load it into a tensor. We can do the same for text. You have some URL, you just call .load, and you have your transcript as a string. All right, so we can look at the, I'll run the same cell again. Let's run this. Okay, I can look at the podcast, what it looks like. Okay, we have an audio URL. This one, we have a tensor, so already loaded in. You can see this is the shape of the tensor, torch float 64. We have a URL to our text, and it loaded in the text as a string. Or say, can you see, and so forth. All right, you can look at the tensor here again. Yeah, selected the, you can see we loaded this tensor from just the audio URL. You don't need to learn about any audio libraries, anything like that. You just have the data types right there in DocArray. Okay, so that's pretty cool. But what makes this really suitable for machine learning is that we can represent batches of data. Usually, when you put something through a machine learning model, you don't just want to put in one data type. You have an entire batch. So what we needed to do is we needed to extend this notion of Pydantic, of representing your data models. We need to extend that along one dimension. So you can have an entire batch or vector of your models. So this is exactly what docvec does. It's a document vector, a vector of documents that you can pass straight into your machine learning model. So let's import some of that. And then we can create a document vector. We pass it a bunch of podcasts that we've just defined, and then we'll create one batch of podcasts. And you may notice this slightly weird looking syntax here. So we have the document vector and then the square brackets of the podcast. And the podcast, just to remind you, is the thing that we just defined as our data model. And usually you don't see these square brackets in a runtime context. You may have seen them as like optional of some type in your type hint, but it's not really something you usually see at the runtime context, so you might need to get used to the syntax, but I think it's actually really nice. Because what this allows us to do is when we extend our model alongside this one dimension, then we can still access all of our user-defined fields. Like we had an audio tensor in our podcast here, but if we have a batch, if you have an entire vector, we still want to access all of our custom-defined properties on that vector. All right, so let's take a look at this. So as I said, we have this vector. We just give it 3 podcasts. Oh, crap. Okay, this didn't work. Sorry? Yeah, something's wrong. I don't know. Ran this morning. Let's just try to rerun. Okay. All right. Oh, it seems to have worked now. Okay, I don't know what happened, but not a bug, luckily. Something with running cells out of order, I guess. Okay, what you can see now, we have like this podvec, a vector of podcasts, and we can still access our audio tensor on this entire vector of podcasts. What we can see here, it actually stacked those up into one big tensor. So it's not like really a list-like thing where each and every tensor would be its own place in memory and they would be scattered around. No, this is actually stacked up into one tensor in sort of like a column-wise manner. So we can look at the audio tensor and at the shape, and we see, okay, it's 3 of them because we passed 3 podcasts, so like the batch size, and then just the dimensionality of each of those examples. And once we have that, we can process this in a machine learning model. Yes, is a question?
Do you mind if a question?
Sorry?
Do you mind if a question?
Go ahead.
So regarding this square bracket podcast,
Yes, this year.
pull the type of the first argument, for example?
Yes.
It's a bit of, I don't know, maybe templating or something in C++ where you don't have the inspection capabilities, but here you have them.
Yeah, so we could have, of course, the question was why do we pass the podcast here in the square brackets instead of just taking it in as the first argument?
No, sorry.
No?
Instead of pulling it from the first argument, so you can just do from the instance that you get, you can do under class or something to get the actual type.
From this here? Yeah, we could do that, but there's actually there's a few reasons. One, we want to be able to use this as a type hint somewhere. So we want to be able to put this in like a function definition or somewhere else to say like this is actually what we need. So I think it's nice to have these like in the same way. But actually you don't need to do this, right? If you want this ability of being able to access all of your fields along the entire vector, then you need to tell the vector what it represents. But if you don't need this, then you can want to maybe put different models here, like a podcast and a video, for example, and want to put them in the same vector for whatever reason, then you can do that. Then you just omit this, and then it would still work. So if we just look at the first one and then pull out the type, then we make an assumption that like we take a choice out of the user's hand because they may not need or want this. That was sort of the reasoning behind that. And you will later see that we use a similar syntax for other classes, where we really can't do anything else, I think. So it also makes sense to keep everything like coherent within the sim library. Okay, so once we have this vector, we can process our data using a machine learning model. And this is just a dummy model, but it I think it conveys the idea. So what this does, it's just like one linear projection, and it takes an audio tensor and produces an embedding. And again, you can see the type hints here, which I think are really nice. You take a torch tensor with a batch and the length, and then you get back an embedding of dimensionality 512 for each of your examples. So this was run already, so we don't need to run it again. So we instantiate the model, and then we can pass our audio tensor to the model. We create embeddings, and then reassign those embeddings to the pod vector, so like all of our podcasts. And again, here it shows that it's really nice that we extend this Pydantic idea along an axis, because you don't really need to reason about your examples anymore. You have your schema that you defined, and you can use it along this axis as if it was just one example. You just pass things around, access, assign, no problem. Okay, so that's it for the representation part of the library, I would say. Okay. Then, as I said, there were 3 pillars of DocArray: representing, sending, and storing. So let's now look at the sending part. And what is really nice about DocArray is that it integrates very seamlessly with FastAPI. So as I said, we want to build like a dummy service for transcribing and searching for podcasts over the web. So what we do here is, again, some imports, FastAPI notably, and then we can process our data here. So we first define an output. We could, again, obviously, again, use the podcast and just return the podcast. But in this case, since we are interested in semantic similarity and transcription, we don't need to return everything. So what we return is just an embedding and a transcript. Okay, this is our output. Then we can create a FastAPI app using this. And if you know FastAPI, you know that you just put in a Pydantic model as your type hint, and it will then use that for your API specification. And in this case, since everything is fully compatible, and since every document coming from DocArray is in fact a Pydantic model, you can just use podcast here in your type hint and output doc as your return, and FastAPI will just work with it. So let's take a look at what we're doing here inside of this app. So again, the user might send us a podcast. This might just have a URL and no audio tensor yet, so we load it. We pass it through the model. We have this dummy transcription model here. It's not doing anything real right now. It just says this is the transcript of your podcast, but you get the idea. You can like call Whisper or whatever you want here, and then put it into the output doc and return it. And then we can spawn our web server and run it. So this was also, oh no, that's not what I wanted to do. Okay, so now we can actually call this API, and I have this here. Paste it in. Okay, what do we get? We get an output doc with an ID. It has an embedding, so these are these 512 numbers that represent this podcast in a sort of semantic way, and the transcript. This is the transcript of your pod. Okay, so that's cool. So we can kill this. All right, so that's how you can send data with DocArray, because it just serializes all of your torch tensors or your NumPy arrays or like your data, as we take care of all of that, and then it just slots into FastAPI. But actually, another thing that it can do is serialize to protobuf and be sent over gRPC. Then you wouldn't use FastAPI anymore. Then there's Gina, the library that gave the name to the company that I work for, which is sort of a similar thing, but it as I said, works over gRPC with protobuf, so it should be more efficient. It also has some features like dynamic batching, so if you want to take inputs from multiple users or from the same user and batch them together before you pass into the machine learning model, then Gina can do that for you. So if you want to, or if you send big tensors around, then HTTP is quite slow, and you may want to use protobuf over gRPC to make that faster. And again, then DocArray would just slot into that seamlessly. Okay, so that's for sending data, and the last thing is storing data. So, as I said before, in this machine learning paradigm, also for storing data, you might need new tools and new libraries, new databases. And one example of this is vector databases. And what vector databases allow you to do is you store your embeddings or any tensors, and then you can do very fast similarity search over those tensors. So for example, in the app that we're currently building, I have some podcasts, and then a user gives me another podcast, and I want to find similar podcasts. One way to do it is pass the audio of the podcast through a machine learning model that produces a vector. I store all of these vectors in the database, and then when the user query comes in, I do the same, and I have these vectors, and I compare which in my database is the most similar vector, and I return it. This is what these vector databases let you do very efficiently. And they're also very useful for things like giving long-term memory to large language models. Maybe that's, someone mentioned LangChain before. It uses these vector databases to sort of enhance or like increase effectively increase the context size of a large language model, again, by storing these embeddings and then doing similarity search on these embeddings. So for our web app here, what we want to do is whenever someone sends us a podcast, we want to store it, or like its embedding representation in our vector database. And then when another user wants to find a similar podcast, we do a lookup and return the most similar podcast that we've seen before. So you could imagine if someone sends in the same podcast episode, we don't need to transcribe it again. We just look, have we seen this before, pull it, and return it. So we import here this HNSW document index. And as you've seen here, DocArray currently supports a bunch of different vector databases, all with the same API. So right now it's Weaviate, Qdrant, Elasticsearch, and HNSWlib. And HNSWlib is just meant as like a local, small, lightweight alternative if you don't need a full-blown database. So that's what we're using here, the HNSW document index. So we can instantiate that. And again, we have this square bracket notation with a podcast. And here, actually, we see why we need this information here right away. Because in the database, we need to have a schema or like a table or with the columns in our database, etc. So, but you don't want to do that yourself manually. You don't want to think about, okay, I have my data model in DocArray. How do I map that to the database? What column types do I choose? Maybe to just get started quickly, you want this to just work. And this is effectively what these document indexes let you do. So you just have your HNSW document index, parameterize it or template it by podcast, and then it will, in the database, create the columns accordingly. And here we pass basically a working directory for it because, as I said, HNSW is just a local library that runs. If you had Qdrant or Weaviate, you would just give it the host and port of your database, and it will just hook into your database instance and work there. So we can instantiate this here. So now we have our lookup database for our podcasts. And we can put that together into our web app now. So I'm creating a new API endpoint called transcribe and index. So again, we created transcriptions for our podcast, but we also store that away in our vector database for lookups in the future. So it's the exact same thing, except for this one line. This is the new thing here. Doc index, the document index we just defined, and then we index our podcast. And there's a whole lot of other things that you could do with the vector database, but in the simplest case, you just want to store your data away. And as you can see here, with just like 2 lines of code, you have a vector database with the proper schema for your data, and you can index it in there very easily. So we can run this and start a server again. So let me see. So let's, again, what we need to do, we need to send this to a different endpoint. Transcribe and index. Boom. Same result. From the user's perspective, it's the same. But of course, on the server side, we've now indexed this document in our vector database. And then I've created another endpoint, find. So if a user just wants to find a similar podcast to what they have, they can send their podcast there, and we will do a lookup in our vector index to see what we have here. And here, again, we just create embeddings, same thing we've done before. And the important line here is this one. So we look at our document index, and we want to find similar stuff. So we take the user input, we say, okay, how do we even want to compare this? Because now our podcast only has one embedding. But if we think more generally with multimodal data, I might have multiple embeddings. I might have an embedding for my audio and for my transcript, for example. So I can choose where do I search, what is the basis of comparison between the user query and the database. In this case, we say embedding, it's the only thing, but we specify, okay, embedding, you look at the embedding field of the input and the database, and then you compare and pull out only one result. In this case, we just want to get the most similar podcast that we've seen before. Okay, what can we do now? Again, oh, wait. Something's messed up here a little bit. That wasn't supposed to happen. Okay, I've done enough troubleshooting on stage as is. The idea is you should send your podcast and get the most similar one back out. Something's cursed, I don't know. I promise I've tried this morning and it worked. I'm not sure what happened. Yeah, so that's the third part of the library, the store part of storing things in a vector database for efficient retrieval. Okay, so let's just sum up these ideas of typing in the machine learning world and of what DocArray is trying to do. So you can see sort of a progression here. Before Pydantic, FastAPI, and SQLModel were a thing, you sort of did manual validation because Pydantic wasn't a thing. You, instead of using FastAPI, you used Flask, but now maybe you like these types, so you use FastAPI. And instead of using SQLModel, you may have used SQLAlchemy. Does essentially the same thing, but doesn't have this nice API, this nice user interface that SQLModel has. But now if you make another step and move into the machine learning world and want to serve machine learning applications or just train your models, then you need to make another step, I think. And this is what we try to do. I hope it goes better in general than it just did during the demo, but I'm confident. So instead of using Pydantic, you may want to use DocArray. So you can have your machine learning-centric types. Instead of using FastAPI, as I said, it's still a very good tool for many use cases, but for some use cases, you may want to use Gina for gRPC and protobuf. And instead of using SQLModel, so if you don't work with the SQL database, but instead with the vector database, then you may want to use DocArray to talk to your vector database. This is sort of the thing that we try to achieve here. Okay, that was basically it. As I said, type hints are entering Python left and right. I think they are the future for the language, at least on the user interface side of things. I think they make for really nice APIs. That's why we are pushing on their usage in DocArray. I hope you all give it a try. You can find it on GitHub, give it a star, or at least check it out. Yeah, thanks for your attention, and thank you. Yeah, if you have questions, I'm happy to answer. Yeah, there's one right here.
Can you make these slides available online somewhere?
Yes, of course. Yeah, I think I'll put them in the repo somewhere. Yeah, so if you look at the repo, they will appear there. Yes.
Great presentation. Still,
Sorry, could you speak up a little bit?
can you hear me?
Barely.
Yeah, so I said great presentation.
Thank you.
Still new to the Python world, but does DocArray support generics?
Sorry, what is happening? Someone's pointing.
DocArray supported.
Yeah. There's a microphone back there. That's what I'm. Okay. So the question was, does DocArray support generics? I'm not. So in the type hints, you mean?
Yeah.
Yes. You can do so because we built on Pydantic. Anything you can do there, it will just work. Read on the like this model base model kind of idea. We really just add our types on top. Make sure that they are fully compatible with Pydantic, and Pydantic can take generics and all of that sort of stuff, so it will just work, yes. Yeah. Any more questions? Yes, here. The microphone is coming.
Okay. Like my question is about the data typing for images and text and data. It works with multimedia files stored in cloud providers like Google Cloud or AWS?
Yes, yes. As long as it can be reached on the web somehow, it works.
Okay. And secondly, for example, you have a generic method called load. For example, in the case of images, you can load using Pillow or NumPy. Can you specify the type of how you load the image, or is not?
The type, what do you mean by the type? What you get, if it's an array or a torch tensor, is that what you mean?
Yeah.
Under the hood, for images specifically, we load with Pillow. And then what that will give you is a NumPy array. But if in your document, you specify a torch tensor, and then assign a NumPy array to your torch tensor, then it will convert it automatically. So this is the same idea that we've seen at the beginning, where in Pydantic, I had this user with an ID that was an int, but I passed a string. And then Pydantic coerced the type to integer automatically. And in the same way, if you use DocArray and have a torch tensor and pass an ND array, we will just coerce it for you. Or even if you specify shape 256 and you pass a thing that's of just shape 512, then it will automatically reshape the thing, which I think is really nice. So you just declaratively say, this is what I want, and then it will reshape it in the best possible way to make it work.
Okay, thank you, and congratulations for the presentation.
Oh, thank you.
Thank you for your presentation, first of all. I would like to ask, what about the dependencies for the library? Because as you showed that there's a bunch of different stores that you support, guys.
Mm-hmm.
Does it mean that if I install DocArray, I'll get all the libraries like Elasticsearch and all this stuff, all this kind of jazz in my project?
God, no. So we have different install options. I think the base install is quite lean. I'm not sure exactly what's there, but NumPy for sure. I think Protobuf. I'm not sure if Protobuf is there by default, but it's not much. And you sort of decide at install time what you want. You can say pip install DocArray, square brackets Elastic, and then it will come with Elasticsearch. Yeah.
Okay, thank you.
All right. Any other questions? No? Okay, then thanks for those questions. And if someone wants to come up to me and talk in person, I'm happy to do so. Also we have a booth downstairs, the Gina booth. What's the number? 405. 405, and we're happy to talk to you there. And we have swag. All right.